So in this section, we're going to learn about the three most common types of nuclear radiation. Now, the word radiation is a scary word for many people. It simply means that something that is spreading out from a central source. We're exposed to radiation all the time. We have radiation coming from the sun. That's the light radiation coming from the sun. Of course, usually when people talk about radiation, they're often talking about ionizing radiation, kinds of radiation that can damage your cells, for example, causing damage to your DNA. And that is the possibility with each of the types of radiation we're going to talk about today, alpha, beta, and gamma. But we are exposed to these kinds of radiation all the time as well. If you want to get an idea of how much radiation you're exposed to just in your everyday life, you can go to this website, and they have a little calculator there that you put in some numbers, and it tells you about how much radiation you're exposed to in a given year. Now, the kind of radiation we're talking about here is associated with radioactivity. Radioactivity is something when certain elements will spontaneously decay into other elements, and when they do so, they often release different kinds of radiation. An unstable nucleus can spontaneously break apart. That means it doesn't have to have an incoming neutron or something like that, like we saw when talking about nuclear fission. It'll just spontaneously decay into other particles and release energy in the process. Now, nuclear decay is a quantum mechanical process, and so we cannot predict exactly when it's going to happen. All we can do is say what is the probability of it occurring in a given time interval, given a certain number of atoms that you have. The three main types of radiation we're going to learn about in this class are alpha, beta, and gamma radiation. Alpha radiation, the symbol is Greek letter alpha, is essentially it's a helium nucleus. It has a +2 charge because it has 2 protons. So if you have a nucleus that is giving up an alpha particle and decaying into something else, the new particle will have a mass number that has gone down by 4 because it gave up 2 protons and 2 neutrons. Beta decay, if you have something that is giving up a beta minus, that is essentially an electron. It has a charge of a -1 elemental charge. So it has basically the same mass. Of course, in any reaction, if you give up energy, you're giving up mass. But it does form a new element. It is the number of protons in the nucleus that determines what element you have, and by conservation of charge, if you're giving off a -1 charge, then you must have gained 1 proton in the process. And so you're going to have 1 fewer neutrons and 1 more proton in your nucleus. In gamma decay, you're just going to give up a photon. Typically this happens, a photon will be emitted when a particle undergoes some other type of decay and it becomes an excited form of an element, and then the nucleus will fall back down into a lower energy form, giving up a photon, just like we saw when we learned about atomic physics.
Hello. Today's lab concerns the differences between alpha particles, beta particles, and gamma rays as far as their ability to penetrate materials goes. I have a radiation monitor set up, and the radiation monitor is connected through a LabQuest unit to a computer with Logger Pro on it. Nice big screens that you should be able to read it actually from that distance that you're at right now. And what we're going to do is we're first going to try to get a background radiation reading. So now the way this works is you just press collect, and it starts to time for you, and it counts how many radiation impacts it gets in that time interval. Usually it's set up for 50 seconds right now. 50 seconds is a nice in-between time to use because it's long enough that you can average out the random variations in radiation coming from your various sources, but it's short enough time that you can do multiple runs in a day. You don't have to wait hours to see what's happening here. So what we're going to do is we're going to watch this for 50 seconds, and then up here, once it's 50 seconds is up, it'll come up with how many radiation counts it had in that 50-second interval. That means how many different alpha particles, beta particles, or gamma rays impacted on the device, and it was able to take count of them. And it counted 18 counts. That's going to be our background level today as far as radiation is concerned. We need to take that into account if we get radiation coming from our sources, that we subtract that out. Okay, so first up is Polonium-210. This was manufactured in May 2019, and it has a half-life of 138 days. And the polonium is actually inside of this little piece of metal right there. As you can see, there's a little strip of metal inside of there. We're going to put this next to the radiation counter, and each time I'm going to put it in the exact same position as I did the previous time. And once I get it set up, I'm going to use this little box over here actually to kind of keep it in the same position throughout the run. I could hold it there with my hands, but I don't particularly relish holding my hand in the exact same position next to a radiation source the entire time. So now that I got it going, I'm going to say, and it's going to start a count here. And now we can go ahead and cut out some of the boring parts, and I'll just come back to you once we get a count for the alpha particles here. So we had 941 counts in the 50 seconds that the alpha particle emitter was up there by itself. Now we'll take that away and we'll put some paper in between the counter and the alpha source. Put the paper right there, push this right up, try to get it in the exact same position as it was previously. And push this up here. Pull the paper right there. Push that down. Just let me move it until it's in the same position as it was before. There, I think that's about right. And I'll hit collect. And this will be the alpha source with paper in between. Okay, we're back now, and we see we had 13 counts. Now that's actually a little bit less than our background radiation. We may have actually shielded our device from some of the background radiation, which may have been a few alpha particles. So anyways, not much more radiation, or actually less radiation than with the just the background. So we can pretty much say that it's been shielded for radiation, but just to make sure, so we can be consistent, I have a 4-sheet thick piece of aluminum foil here, and we'll put that back in the same position as the others. And hold this up there, hold that in the same, let me put this up there, trying to hold it in the same position as the other source was. There we go. Okay, it appears to be in roughly the same position now, so I'll hit collect, and we'll let it go. And we're back. We got 5 counts with the aluminum foil in there, so even less than with the background radiation just by itself. So now we'll try a beta emitter. We'll put the alpha emitter over here, and we'll bring in some strontium-90. I'm going to get smart now and hold the strontium 90 in position using a little piece of tape. That way I can be sure that I have it in the same position every time. Just make sure it's at the very bottom of this box. And then we'll hold it up right here. And just looking at it there, looks like it's in the same position. I think you can hear from the counter that it is already, definitely has more beta particles than the alpha emitter had, alpha particles. Let's go ahead and press start though. We'll collect. And we'll see what happens here. All right. Hopefully you can read the number, but if not, I'll read it out to you. It's 15,209 counts in that 50-second time interval. Now we'll put some paper on top of that and make sure it's back in the same position as it was before. And hit collect. And we'll cut out the boring parts again. And we're back. Wow, we even had a little bit more radiation this time with the paper in place. Sometimes that can randomly happen, or I may have shifted slightly the position. It's 20,018 counts. We'd have to make very sure that we got the position exactly right if we were going to try to get a quantitative idea of how these different radiation sources are, especially if you're trying to measure the half-life of them. But just get a rough idea of how much radiation can penetrate various materials. You saw there was, not only was it not less, there was actually more here, so probably paper is not doing much at all. Let's see what happens when I take the paper away and I put in my quadruple layer of aluminum foil. And again, try to put it in roughly the same position. I hope it is. And hit collect now. And we'll see what's going to happen, if anything. Okay, we're back. And you see we've cut it down to 14,037 counts. And if I continued on with the aluminum foil, I can make it thicker and thicker. Eventually, though, it would get down pretty far. Aluminum foil is a good blocker for this radiation. In fact, to double check that, let's go ahead and just fold it over one time. We've got time to do that. And we'll put this back up here and try to get it in the same position as it was before. But now with a octuple layer of aluminum foil. Okay, we're back. As you see, we managed to cut it down from 20,000 with no shielding to 10,062 counts with shielding. So apparently aluminum foil is a fairly good blocker of beta radiation. Now let's take a look at gamma radiation. First we'll do gamma radiation by itself. Gamma radiation, we're going to use the cobalt 60 source. Again, I got to locate this so it's in the exact same position each time, hopefully. Remember, we're not looking for the absolute number of counts, we're looking for how much each material blocks it, because that's what's going to matter. We don't know. This radiation source may not be as rich a source of gamma rays as the other source was of beta particles, for example. But what we're concerned with is what happens when we put paper in there and put aluminum foil in there. So let's take this one out and check it out, Okay, we're back. So the gamma source with nothing blocking it is 3,892 counts in a 50-second time interval. Now let's take some paper and see if paper blocks those gamma rays at all. Again, try to put it in the same position as I had the other one. And we'll hit collect. And here we go. And we're back. And it looks like, again, it hasn't blocked it at all. In fact, randomly, it's just a little bit higher than it was with the no paper. It's 4,197 counts in 50 seconds. Now let's try our octuple layer of aluminum foil and see if that helps things out at all. And hit collect. Again, trying to make sure it's in the more or less same position. And here we go. And we're back. And we have 3,097 counts. So a slight decrease there perhaps, but not a lot for an octuple piece. In fact, gamma rays can usually penetrate most metal. That's why they're used in applications where you want to say, that's just like we use X-rays, look inside of living tissue. We can use gamma rays to see inside of metal shipping containers, for example.
So by very careful measurements of the mass of the particles involved in a radioactive decay, we can determine how much energy is released in the process. Say, for example, we have a uranium-238 being converted to thorium. Here you see the atomic mass of uranium-238, and when a uranium-238 undergoes radioactive decay into thorium, it gives up an alpha particle, otherwise known as a helium nucleus. So given these masses here, go ahead and calculate the energy that is released. Now you'll get the masses in atomic mass units, and then you have to use your conversion factor, which is found in your formula chart, in order to convert that to the energy in electron volts. So let's do another example. This one is for beta decay. You are to determine the energy that is released when a thorium-234 is converted into a protactinium-234. Now, since the atomic mass number didn't change here, this is an example of beta decay. It's a beta minus decay. The protactinium has one more proton than thorium does. Now, this particular protactinium atom, though, since it has the same number of electrons it has that thorium had, is only going to have 90 electrons. But the neutral protactinium atom would have 91 electrons because that's how many protons it has. And fortunately, we are given atomic masses for isotopes in terms of the neutral atom. So we don't have to worry about accounting for the extra mass that the beta particle took away, that is to say the electron, because that's accounted for in the fact that we're given the mass for the neutral protactinium, but the mass we actually have would be the protactinium minus one electron. So it's all taken care of there. Figure out the difference in masses here and convert that into the energy that is released in this beta decay. So as we said, gamma decay, you usually have an excited nucleus. Usually it's formed from some previous radioactive decay process. That's how you end up with having a nucleus that is in an excited state, just like an atom can have its electrons in an excited state. When those electrons fall down to a lower state, they give up energy. Same thing happening here. You have your atom, your nucleus in an excited state, and when the nucleus reverts back to a lower energy state, it gives up energy in the form of a very high energy photon called a gamma ray. So determine the frequency of 186.186 mega electron volt gamma ray photon emitted by radium-226. Now, you do have on your formula chart an energy conversion that you can use. You have a Planck's constant given to you in electron volts. So you can use that one to determine what the frequency would be since you're given the energy here. Here is the graphic for you to show you kind of what's going on here. Here are some uses that we use for nuclear radiation. We can date samples of things that were once living by determining how much of certain carbon isotopes they contain. We'll talk more about that in the next section. We can trace the pathways of chemical reactions by putting particular isotopes of certain atoms in our chemical reactions and following those isotopes through. We can use it for radiation therapy, such as using gamma rays to kill cancers, and we can stop food spoilage without having to heat the food up. We can sterilize medical equipment. We can involve non-destructive testing. We can test welds and things like that by using gamma rays to make sure that they are functioning correctly. Radiation is used in smoke detectors and security scanning, like being able to look into metal shipping containers. And of course, in nuclear power. So let's answer this radioactivity question. If you have radium-226 and it's being converted into a radon-222, what else must be involved in the products of the reaction? Go ahead and stop the video, and once you have an answer, you can start it back up again. Well, this is clearly an alpha decay because you have lost an atomic mass number of 4, and that will be provided by the helium nucleus. So the helium nucleus is the other thing that should be listed in the products.